Hey everyone, I'm Mr. A, and today we're going to talk about ellipses. Ellipses are one of the conic sections, those being the parabola, circle, ellipse, and hyperbola. In this video, we're going to talk about them both from a conic section point of view and also from the definition as a locus of points. First, let's talk about what it means to be a conic section. If you take two vertical cones and you invert one and put them tip to tip, then you intersect that cone with a plane, you get a conic section. The most simple one is a circle, which is when the plane is horizontal. By moving the plane up and down, you get larger and smaller circles. As we start to tilt the angle of that plane relative to the cone, then we get ellipses. And again, by moving the intersecting plane up and down, we can get larger and smaller ellipses in the same cone. As we start to increase the angle of that plane, we continue to get ellipses until we get a parabola right at the moment when that plane is parallel to the cone, and if we continue tilting it further and further, we get hyperbolas. So the hyperbola, the parabola, the ellipse, and the circle are all part of this family of relations we call conic sections because we can generate them by intersecting a cone with a plane. And while that connection between conic sections and those four shapes is really interesting, we can get a better handle on ellipses and how we generate the equations and work with them by using what's called the locus definition of the ellipse. So in geometry, a locus means a collection of points that all satisfy a particular condition. For the locus definition, what we do is choose 2 points in space. We call those the foci, F1 and F2 of the ellipse, and then we look for all of the points in space where the sum of the distances between that point and the first focus, and that point and the second focus is a constant. So in this case, that constant is 10. You can see here in red I have the distance to focus 1, and in blue I have the distance to focus 2. And those are both 5 right now, so the sum of the distances is 10. The way we get the ellipse is by asking the question, where are all of the other points on the plane where these two distances are also going to sum to 10? If I start to drag this point, you'll see that it doesn't trace a straight line, it gets curved, and this turns out to be an ellipse. There's a classic experiment you may have seen in earth science where you take a string and you put 2 pins in the paper and you pull the string tight between the 2 pins. That effectively is the fixed distance. The length of the string would be this triangle here, and then you just pull your pen tight to the string and you drag your pen around and it'll create an ellipse. And you can see that as I pull it around, those two distances always sum to 10. So the shape of the ellipse is determined by 2 things: the distance between those 2 foci, F1 and F2, and it also depends on the length that we choose. So if I bring the foci closer together, it changes the shape of the ellipse. In fact, you'll notice it becomes more circular. If I push those foci further apart, you'll see that it becomes less circular, more elliptical, if you will. By the way, you might want to ask yourself what happens if you bring the 2 foci together. Well, should be no surprise that there we get a circle. Of course, the sum of the distances is fixed. It is double the radius of the circle. So a circle is actually a special case of an ellipse where these 2 foci are brought together. Since a circle is a special case of an ellipse, it should come as no surprise that there's a pretty strong connection between the equations. Normally, I wouldn't show you an equation this quickly. I would want to derive it first from the definition. In this video, I'm going to turn things upside down a little bit. We're going to work with it, notice some interesting properties, play with it a little bit, and then at the end, I'll show you how we actually get that from that locus definition. On the left here, we have the equation of a circle. For now, I'm going to keep everything centered at the origin, just to make the equations simpler to look at. Everything that I'm talking about, though, is applicable to any ellipse and any circle. Normally, we write the equation of a circle as x squared plus y squared is r squared, where r is, of course, the radius of the circle. The equation of ellipse looks like this. Now, that's always going to be 1 for an ellipse, and these are going to be 2 different numbers. The reason they're different is because an ellipse has a different radius in one direction as it does in another direction. If we were to divide everything over here by the radius squared, we would get the equation of a circle, but looking much more like this equation of the ellipse. There's a connection to be made here. In an ellipse, the a is actually the radius in the x direction, and this b is the radius in the y direction. For a circle, of course, the radius is the same in all directions. So it's still true that this is the radius in the x direction and this is the radius in the y direction. It's just that they're the same number, so we just have one single radius. Let's talk about what I mean by this for a minute. Let's consider an ellipse that is wider than it is tall. And as I said before, we're going to center our ellipse at the origin. If I wanted to find the x-intercepts, I would set y equal to 0, which would make the y term drop out of the equation because 0 squared over b is just 0. X squared has to equal a squared, which could only happen if x was plus or minus a. By the same token, to find the y-intercepts, I would set x equal to 0. Cross multiplying, we get y squared equal to b squared, which means y is plus or minus b. If you look at this graph now, you'll see that from the center of the ellipse, it's a to the right and a to the left. That's what I meant when I said that it's the x direction radius. And if I go up and down in the y direction, it's a distance of b. So b is the y-axis radius. Now, it's not always true that a is the x-axis radius. What's always true is that a is larger than b. The reason we do that will become apparent in just a few minutes. But for now, what I want you to understand is that whatever fraction the number is in, it's always the radius in that direction. Whatever's under y squared is the radius in the y direction. Whatever is under x squared is the radius in the x direction. Just make sure that a is always the larger number. You have to remember that. And the reason we do that is we call 2a the major axis, meaning a is the semi-major axis. Every ellipse has one longer direction and one shorter direction. We choose to make that longer direction always be 2a. And then 2b is the minor axis, which is the shorter side of the ellipse. What about those 2 points that we measured the distance from? It turns out that the coordinates of the foci are given by another variable, c, and it's always the difference of the squares of a and b. c, 0 would be the coordinates of one focus, and negative c, 0 would be the coordinates of the other focus. In order to understand where this relationship comes from, we have to take a look at 2 moments in time on the ellipse. If I look at a point on the ellipse that is directly above the center, we know from our discussions earlier that this distance, the semi-minor axis, is b. This distance from the center of the ellipse to the focus we'll call c. This is a right triangle here since I went straight up, but we don't know what the hypotenuse is. But we can figure it out if we remember how the definition of an ellipse works. Remember that the sum of the red line and the blue line's distance has to be the same, no matter where I take this point on the ellipse. So if I drag this point over here to one of the ends on the major axis, notice that the red distance goes from the focus all the way across to this side of the ellipse to the point. The blue distance is only right here. Because of the symmetry of an ellipse, that distance has to be the same as this little missing piece over here, which means if I call the red length d1 and the blue length d2, then over here we can see that d1 plus d2 span the entire major axis of the ellipse. d1 plus d2 has to be equal to 2a. Remember, the major axis all the way across the ellipse is always 2a. That's that constant sum we were talking about in the beginning. So when I go directly up to this point, d1 is equal to d2 because of the symmetry of the ellipse. It's the same on the left as it is on the right. So in this moment in time, we can see that d1 is exactly equal to d2, which means that they're both equal to a because the sum of them has to be 2a. Now we can use good old Pythag to see that in fact c squared plus b squared must equal a squared, which gives us c squared equal to a squared minus b squared. To move an ellipse to a center h, k, we simply replace x with x minus h, and we replace y with y minus k. This would describe any ellipse where the major axis is parallel to the x-axis. So here a is our x direction radius, and b is our y direction radius. Over here, everything is the same except that notice the a and b have switched. Now a, the larger radius, is in the y direction, so it goes further up and down than it does left and right. All of these coordinates here are pretty simple if you just think through them. If the center of the ellipse is h, k, you know that c is the distance to the foci, so h plus c, k, and h minus c, k will get you to the foci. H, k plus b and minus b will be the co-vertices, and h plus a, k, h minus a, k would give you the major vertices. Armed with all of that information, we're ready to solve some problems and actually graph some ellipses. Here we're being asked to rewrite this ellipse in standard form and sketch it. So the first thing I'm going to do is collect terms together. I want to get my x squared and my x together, and my y squareds and my y's together. And I want the constant to be on the other side by itself. If there are any leading coefficients on the squared terms, there's 9 on the x, but there's a 9 on the y squared, I want to factor those out. Now we need to complete the square in order to get this to look more like the standard form of an equation of an ellipse. I'm going to assume at this point that you're familiar with completing the square as a technique. If you're not, I'll put a link in the description to a video I have all about completing the square. That video explains everything you need to know about completing the square. Here I'm just going to kind of run through it and assume that you understand what I'm doing. So I'd like to replace this x squared plus 6x with some quantity squared. I know I need an x to be in there because I need an x squared. In order to get the 6x, I need to put a plus 3. Think about why that'll work. When I multiply this binomial by itself, I'll get an x times x, so that'll take care of the x squared. I'll get 3x twice, because I'll have the first x times 3 here, and then 3 times the x there. That'll give me the 6x. But I've added something that wasn't there because I'll have a 3 times 3 as well. There'll be an extra 9 here. So when I replace these two terms with this one term squared, I've added 9 to the left-hand side. That means in order to keep this equation balanced, it's no longer going to be equal to negative 225. I have to add the same 9 that I added to the left-hand side to the right-hand side. If that doesn't make sense, go and watch that video on completing the square. It should clear that up for you. The same thing with these y terms here. I'd like to replace this with 9 times some quantity squared. I need this to give me a y squared and a negative 10y. Well, the y squared's easy. I need a y. To get the negative 10y, I need a negative 5 here. The reason is, when I square this binomial, I'll have negative 5y and then another negative 5y to get me that negative 10y, but I've also added an extra 5 squared to the left-hand side. You might think, well, that's okay, we'll just add 25 to the right-hand side. But be careful. With an ellipse, you're often going to have a coefficient outside of this binomial. There's an extra 5 squared inside of these parentheses. That's going to be multiplied by 9. So it's really 9 times 5 squared that I'm adding to the left-hand side, which is to say 9 times 25, or 225. I need to add 225 to the right-hand side so that everything balances out. Now that I've completed the square, I'm going to do a little bit of collecting terms. That'll give me x plus 3 squared plus 9 times y minus 5 squared equal to 9. And remember, I don't want this to be a 9, I want this to be a 1 for the equation of an ellipse. So I'll divide everything by 9. There's my equation of the ellipse in standard form, and once I get it into this form, it's a pretty easy task to go ahead and sketch the ellipse. The first thing I want to do is figure out what a, b, and c are. Remember that a squared is always the larger number, so in this case, a squared would be 9, and a would be equal to 3. B squared is 1, so b is also 1. Recall that c squared is a squared minus b squared for an ellipse, which means c squared is 9 minus 1, making c squared 8, and c the square root of 8. I'll always simply use the principal root for all of these, because we're going to go right, left, up, down anyway, so we don't need to worry about positives and negatives for these. The only thing left to do is figure out the center. Remember, it's h comma k, where this is x minus h, and this is y minus k. So in this case, the center of our ellipse would be negative 3 comma 5. And now we're ready to go ahead and sketch our ellipse. Since a squared is under the x squared term, that tells us the ellipse is going to open up left and right. The center of this ellipse is going to be negative 3 comma 5. To find the two vertices, we simply go left and right by 3, the value of a, giving us 0 comma 5 and negative 6 comma 5. To find the covertices, those are the points of intersection with the minor axis, we simply go up and down by the value of b. To locate the foci, we're always going to move along the major axis. So since the major axis is left and right on this ellipse, the foci are going to be to the left and to the right of the center of the ellipse, both equally distant, and the distance is c, the square root of 8. To locate these points, then we simply go the square root of 8 to the left and the square root of 8 to the right. Whenever I'm sketching an ellipse, I always find it helpful to sketch out the entire ellipse before adding the x and y axes. This way I don't have to do as much guesswork. So here we have a point 0 comma 5, so we know the y-axis has to go somewhere along that point. And since the y-coordinates here are 6, 5, 4, the x-axis is going to be somewhere down here. It would actually be off my page, but we'll just put it there. This way we can see our two axes. So this entire ellipse lives in the second quadrant. Let's take a look at another example. This time notice we have the x squared and the y squared terms, then the x and the y by themselves. The whole thing is equal to 0. First thing I'm going to do is rewrite this with all the like terms together. Once I have my x squared and x together and my y squared and y together, I'll factor out the leading coefficient on the x squared and y squared term, giving me 9 times x squared minus 4x plus 4 times y squared plus 6y equal to negative 36. Now what I want to do is replace this with 9 times a quantity squared and 4 times a quantity squared equal to negative 36. What do I need to place inside this binomial to give me an x squared and a minus 4x? Well, that would be a minus 2, right? X times x is x squared, minus 2 times x is minus 2x, and the second one will give you the minus 4x. But you've also added something to the left-hand side now. When I replace this x squared minus 4x with x minus 2 quantity squared, I've actually added a 2 squared times 4 to the left-hand side. So I've actually added 9 times negative 2 squared, which is 9 times 4, or 36 to the left-hand side. In order to balance that out, I must add 36 to the right-hand side. Likewise, I want to replace y squared plus 6y with some quantity squared. That's going to be y plus 3 quantity squared. When I square this binomial, y times y is y squared, y times 3 is 3y, another one of those will get me 6y, but then there's a 3 squared left inside of here, which will be multiplied by 4. I've added another 4 times 3 squared to the left-hand side, which is 4 times 9, or 36. To balance that out, I need to add 36 to the right-hand side as well. Collecting terms, I get 9 times x minus 2 quantity squared, plus 4 times y plus 3 quantity squared equals 36. I want that 36 to be a 1, so I'll divide everything by 36, giving me this equation for my ellipse. Once we have the equation of the ellipse, we can see that a squared is under the y squared term, which tells us this ellipse is going to be taller than it is wide. Since a squared is equal to 9, a is 3, and since b squared is equal to 4, b is 2. Remember that a squared is always the larger of these two numbers. Since c squared equals a squared minus b squared, c squared is 9 minus 4 in this case, and c ends up being the square root of 5. The center of the ellipse is always h comma k, where this is x minus h and this is y minus k. So in this case, the center is 2 comma negative 3. Armed with all that information, we can go ahead and sketch our ellipse. So the center here is 2 comma negative 3. To find the vertices, the points along the major axis, we simply go up and down by the value of a. That's 3. So this is going to be 2 comma 0 and 2 comma negative 6. To find the co-vertices, the points along the minor axis, we simply go left and right by the value of b. So that would give us 4 comma negative 3 and 0 comma negative 3. And to locate the foci, we're going to go up and down by the value of c. Since this ellipse has a major axis that's vertical, we're going to go up and down to find our two foci. Whenever I'm sketching an ellipse, I always wait until the end of the sketch to put my axes in. We can see that this point 0 comma negative 3 is on the y-axis, and this point 2 comma 0 is on the x-axis. So this ellipse will look something like that. We denote the eccentricity of an ellipse by the letter E, and it's defined as the ratio of c over a, where c is the distance to the foci and a is the semi-major axis. This is not Euler's number, which is another use for the letter E in mathematics. This is the eccentricity of an ellipse, and you just kind of have to get that from context. The eccentricity of an ellipse is simply a number that tells us some measure of how round the ellipse is. Or perhaps a better way to think of it is how far away it is from round. The numerator is going to control everything about this fraction. A is the semi-major axis, so it's always going to be some positive number. C is going to determine the value of this fraction. Now for an ellipse, it's always going to be less than 1. It is in fact going to be between 0 and 1. And we can see why this is pretty easily. In order for it to be 0, c would need to be 0. So that is to say, the distance from the center to the focus would have to be 0. Let's pull up our ellipse here from before and think about what would happen if the distance from the center to the focus was 0. If I bring the focus closer and closer to the center, notice what happens. My ellipse becomes closer and closer to a circle. At that point, when c is 0, the ellipse is a circle. The two foci are both 0 distance from the center, which is to say they're both at the center, and the ellipse is simply a circle. So a circle has eccentricity of 0. As soon as we start to move those points away though, now c has some positive value. Remember, the denominator is the distance all the way to here, so when the two foci are close together, it's a very small eccentricity, and as I push the foci further and further apart, then that eccentricity becomes closer and closer to 1, because we're taking the distance to the focus and dividing it by the distance all the way out to the vertex. You can probably see where this is going. No matter how far you push these two foci apart, they're never going to quite get to the ellipse themselves. So you're going to be stuck below 1 here. You'll never get to an eccentricity greater than, or in fact even equal to 1. No discussion about ellipses would be complete without mentioning a really interesting property that they have. If you watch the parabola video, then you know that a parabola takes lines that are coming in perpendicular to the directrix and it focuses them on the focus of the parabola. You may have wondered if there's something similar with an ellipse, since an ellipse also has a focus. In fact, an ellipse has not one, but two foci. Unlike a parabola, an ellipse is a closed shape, so you can't get any signals coming from outside the ellipse. Everything has to happen inside of the ellipse. However, it turns out that if you have an ellipse and you send a signal out from one focus, it will hit the ellipse and bounce back off at the exact correct angle to take it to the other focus directly. And we can actually see this by bringing in that same tangent line we did for the parabola. This line here is tangent to the ellipse. It only touches the ellipse at one point. We need calculus to figure out how to get that line, but for now we can just think about what's happening. Notice these two angles again. This is a physical property of reflection, that when you have a signal coming in, it always leaves at the same angle to this tangent line. As I drag this around, you can see that these two angles are always the same. That means that a signal that begins at this focus, no matter what point it hits the ellipse at, it's always going to bounce off the ellipse directly at this focus. One kind of fun application of this is something called a whispering room. If you've ever been to DC, in the Capitol building there's a whispering room, and this is where they actually build the ceiling of the room in the shape of a three-dimensional ellipse. If you stand at one of the foci of that ellipse and you whisper, then someone standing at the other focus can actually hear you while you're whispering, even if the room is noisy and crowded. The reason is because normally when you speak, the sound goes off in all directions, and the person who's listening to you only gets the part that went directly towards them. But when you're standing in a whispering room, the sound that leaves your voice in every direction bounces off some part of the ellipse and ends up at the other focus, which means they hear theoretically every bit of the noise you emitted, and they can hear you whispering in a noisy room. This also comes up in medical treatments. One way they treat kidney stones is by placing placing you into a large ellipse. They set it up so that your body is here at one focus where the kidney stone is. They emit a very strong sound wave from the other focus. That sound wave goes off in all directions, bounces off all the different sides of the ellipse, and then gets refocused right at the point where the kidney stone is, and they can actually use those sound waves to break up the kidney stone because they're diffuse until the very moment they all come together, which is due to this property of an ellipse. The most important things to remember about an ellipse is that a is always the larger number, or really a squared is always the larger number. C squared is always equal to a squared minus b squared, and depending on where that a squared term is, you know whether the ellipse opens up or down, or to the left and the right. You can locate the vertices by moving along the major axis, the covertices along the minor axis, and the foci are always C away from the center. So there you have pretty much everything you need to know about an ellipse in order to work with them and solve the equations and graph them. If you're interested in how we actually get the equation of an ellipse, I'm going to take you through it here. In order to come up with the equation of the ellipse, you have to remember how the definition works. You start with 2 points, which we call the foci of the ellipse, and you choose some distance. Now that distance ends up being the major axis of the ellipse, which recall was 2a. And the fact that 2a equals d1 plus d2 means that d1 has to be 2a minus d2. If we call the points on the ellipse x, y, if the center of the ellipse is at the origin, 0, 0, then the coordinates of the foci will be c, 0 and negative c, 0, so d1 is the square root of x plus c squared plus y squared, and d2 is the square root of x minus c squared plus y squared. Remember, these distances aren't always equal. What is true, however, is that d1 is equal to 2a minus d2, and that's the expression that we'll use here. Since we have radicals on both sides, we're going to need to do some squaring, and this is where the algebra starts to get a little bit cumbersome. So we'll square both sides of this equation. I'm also going to distribute out these binomials. After squaring each side, we have this long expression. Now before we go any further, we have a lot of things to cancel out here. So we've got an x squared on the left-hand side and an x squared on the right-hand side. We've got a y squared on the left-hand side and a y squared on the right-hand side. We have a c squared on the left-hand side and a c squared on the right-hand side. All of these terms are going to disappear. Here we've got a minus 2xc on the right-hand side and a positive 2xc on the left-hand side. So I'm going to add 2xc to both sides. That'll bring them both over here, so I'll have 4xc. I'm also going to subtract this 4a squared so that I can isolate this radical. Since everything has a common factor of 4, I will divide by 4. I'm going to take that whole thing onto the next page and continue by squaring both sides because I still need to get inside that radical. At this point, we have a couple of things that we can cancel out on each side. Having any c terms in this equation is going to be a problem because there shouldn't be any c's left in the equation when we're finished. So we're going to substitute c squared equal to a squared minus b squared. Replacing both of those c squareds with a squared minus b squared and then distributing through, we have an a to the fourth on both sides, so those are gone. We also have an x squared, a squared on both sides, so those are gone. I'm going to do a little bit of rearranging and move things around so I get the constant on one side and the x squareds and y squareds on the left. And do you see what the next step is? If we divide everything by a squared b squared, then we get x squared divided by a squared plus y squared divided by b squared equals 1, the equation of our ellipse centered at the origin. Of course, we can translate that ellipse left, right, up, and down so that it can represent any ellipse on the coordinate plane, but that's how we get the equation from the locus definition. If you enjoyed this video, please give it a like, subscribe to my channel, feel free to leave a comment below, and as always, have a great day.